Yes. Good morning. Again, I going to give the last presentation, which is on one of the joy research activities that we were conducted in the last few months as well. And it is quite different from other presentations that other research joy research activities that have been presented, because in this one we were exploring the potential to use remote sensing, geophysics, and imaging technology in physical modeling, which is quite different from traditional geotechniques. And I must really say that this is not my area of expertise. I was coordinating this, and I got help from all the partners, in many cases from geophysicists or people who work with remote sensing in different partners. So I'm really grateful for that. But it's really opened my eyes to be able to have these opportunities to work with this topic, because it shows that there's so much more than that we could use from other technologies that we could utilize for to deal with the challenge that we have today. I'm going to go to the presentations with some explanations why we want to do these joint research activities, and then basically go through the three technologies that we were exploring: remote sensing, geophysical methods, and imaging technologies, and some conclusions at the end. Motivations, it's very simple. Industry needs more cost-effective and efficient solutions for subsurface characterizations, for detections of utility defects, and for ground monitoring. And we all know, and we all enjoy the benefit of significant advance in remote sensing, because we can see satellite data almost anywhere now. Geophysics and imaging technologies over the last decades. So the pictures on the right, just some pictures that I cut out from NGI website, but we do use this method and offer our service in NGIs in many actually practical projects. So it's not as advanced as it's now, because it is really in applications. The aim of this deliverable was to provide an overview on the use of these technologies in the lab, also in the centrifuge, in the case of imaging technologies, but particularly is for field study. We reviewed the past and existing study which were performed by different geolab partners. Because I guess if we extend to the whole just general literature review, it would be too, the scope would be too big, and so we were limited to that, and also to identify possibilities for collaborations, incorporate innovations in existing research infrastructures. But why are we interested in these technologies? It is also from NGI website. This shows how we are doing today with ground investigations. When I have projects, I order ground investigation, and normally, in most cases, we send out drill rig with people drilling borehole, taking sample, testing the lab. That gives me information about the ground conditions, which give me the basis for design and for decide the next step in our projects. But in many cases, that is quite challenging, because it had to be a road that the jury could drive to come to the point where I want my information. The jury is very costly. Just to start it, the start price is minimum 3,000–4,000 euros just to have the juries. And then yes, there's a lot of challenge with using traditional methods for ground investigations, and it is an image of ERT survey in the fields, which is first, yeah. I forgot to say also, with drilling is very challenging in terms with, especially in urban area, when we think about infrastructures that is underground. So you cannot just go anywhere and drill anywhere. It's a lot of investigation you have to done in advance in order to place a borehole anywhere. And so the idea of having non-intrusive and non-destructive method to find out about the ground is extremely attractive, especially in challenging terrains. And the image shows the ERT surveys that done in one of our transnational access. And for those who's not familiar with it, it's basically they go out in the field with the equipment as the little picture show you, and scan the ground and try to get an idea of what is the ground conditions based on the electrical conductivities that they measure. And the other reason why we are interested in this technology is it can be fast. It's not always faster than traditional method, but many of them are faster. And the possibility to cover very large areas, as these pictures that I just put on, where they show a huge area of London's, we will follow up with I think InStar technologies. So there are a lot of possible applications for geotechnical challenge using these technologies. Just some example which pull out from the contents that were provided to me by the partner. For monitoring deformation and settlement of building and infrastructures, remote sensing. For physical modeling of deformation and settlements in centrifuges, many probably all the partners that have centrifuges in this group have used this, PIVs, as I've learned. Monitoring of landslide and others, then remote sensing, such as InSAR or LiDAR technology have been utilized for quite sometimes. Detecting of objective utilities and defects, geophysical methods is utilized quite widely. And particularly interesting is soil characterizations, which we start to use more and more geophysical method, not as by its own, but as supplementary to traditional boreholes. And this we start to find out can be extremely useful. Okay, now I will give us some example, some explanation and some example about first remote sensing and then geophysical methods and image analysis. Remote sensing is basically detect and monitor physical characteristic of an area by measuring its reflected and emitted radiations at a distance. As you can see here, this is a principle for radar interferometries, which one of the presenters earlier today have talked a lot about. Or InSAR, short for satellite-based radar interferometries. Basically, they emitted a signal to the ground and they measure the reflected signals and do that analysis. It depends on how the wavelength and intensity of the reflectors. They can calculate movement like ground motions as shown in the pictures. And then light detection and ranging, short name LiDAR, is principle is the same. Emits some signal, measures the reflections, but normally it's done on a helicopter, a drone, or sometimes with ground-based LiDAR. Remote sensing have been used in NGI. This example is from NGIs. It will use in dam monitoring. Satellite-based interferometries have still consider an innovative method for monitoring of tailing dams, and in this case, in a tailing dam in Brazil, which fell on the 25th of January 2019. And what my college tried to do is to test the applicabilities of remote sensing in detecting this failure is to obtain data from Sentinel-1, which is a satellite, and then analyze this data for the as you can see, mean velocities like movement at different points along the tailing dams. The conclusion of this study was that there's some evidence that data were able to capture the displacement just prior to failout. And this idea is, of course, is very attractive, but only few points show this sudden movement. So it's a bit inconclusive at the same time. And that is why it is still important to do more research and more testing of these kind of technologies. This is an example about LiDAR, which is the other technologies that I were introducing. This was a project in NGI where they investigate rock faces for potential geohazard issues with terrestrial laser scanner. And as you can see in the process figures, the planes are automatically detected and classified according to orientations based on LiDAR scan, and the thickness of surface layers in meter in tunnels can be visually calculated. It's shown in the figure on the right. Yes, and then the other group of methods is classified under geophysical method, as you can see in the figures. I'm sure many in this group probably know a lot more than me about this, but anyway, the electromagnetic methods, ground penetrating GPR, ground penetrating radar, seismic refractions, microwave gravity, radiation, thermal imaging, and spontaneous potentials. That is basically a class of method where it's non-invasive investigation of subsurface conditions in the earth through measuring, analyzing, and interpreting physical fields at the surface. And the methods that were reported by GeoLab partner, including electrical resistivity tomography, which I have already shown some figures, which measure electrical resistivities. You can also use seismic methods, which measure seismic wave, electromagnetic methods, which measure electromagnetic signal, and ground penetrating radar, which measure radio pulses. So it's classified or different methods based on different type of wave with different wavelengths, as I understand, different type of signal. This example here shows the principle of resistivity measurements through electrical resistivity tomography, short name ERTs. The principle is basically injected a current through electrodes, and the resulting voltage field in the ground is measured with a receiver. It can be used for ground investigations, also for detecting problem, and in some cases it has been used, or I guess a lot of cases, not some cases, that it has been used to monitor, for example, contaminant transport, where the contaminant change the electrical conductivities of the ground. This example is really a nice example from Delta's, where they actually make a small lab ERTs equipment and show how they can detect PE membrane in experiment tanks, as you can see in the figure here. Okay. Here you can see this is a tank with different. There's a white panel is clay, and the rest is sand. And the ERT signals show that they actually can detect the different inconductivities between clay and sand. And the signal that is in terms, it is plotted in terms of electrical resistivities, again depth, and you can see that it's quite clearly show that it can actually differentiate between different materials. And it is, I found it is quite fascinating, because if it can replace all the borehole one day, I think it would be revolutionary in terms of how much information we could get from the ground just by scanning. Seismic surveys. The major type of seismic waves based on propagation characteristic is shown in the figure here. And the principle is quite similar to, basically all the methods that I'm presenting now is quite similar in terms of that is based on emitting some type of wave and measure the reflection with a receiver. And through this measurement, they can detect different conditions. These figures from SERDEC shows, for example, data acquisitions in the field, how they interpret arrival times and layer assignment. And from the signal that they receive, they can build up a layer model with different VP, which would give different interpretations of soil type. Normally, as I found out, most of this method we have to compare with borehole data in the end in order to have a concrete conclusion of which soil types we are looking at if we talk about soil characterization. In this example, they were characterizing marine soils and landfill using different seismic methods in Ibiza, Spain. And the figure just show different tests, basically in a different angle. We have the first figure is the execution of the test. And then we have here seismic light used. And the last one is seismic source used in Ibiza. Ground penetration radar. This is basically an antenna, consists of a transmitter and a receiver, and transmit electromagnetic pulse of radio frequency into the medium. That is the principles. Also sending out a wave, an electromagnetic wave, and then have a receiver to measure what you receive. Like in terms of travel time and amplitude. This figure shows the longitudinal GPR profile from tunnel wall constructed from individual scan. And in a project that our partner in ZAC, in Slovenia, did at the Cassia Monte Mario railway tunnels, they will attach this radar to an excavator, and the excavator is sitting on a flat car which move along the tunnels, and then the radar can scan the whole tunnel. And the purpose is to detect abnormalities beyond the wall surface, such as moisture defects, air void, and delamination that can be examined to the signal analysis. And then we have electromagnetic method, which with the R, because sometimes it's airborne electromagnetic methods. Basically, the principle is also sending out signal, electromagnetic inductions to generate eddy currents in subsurface of a conductive mass. It measures the response of the ground to the propagations of electromagnetic fields. And it is increasingly used for ground in characterization in geotechnical engineering applications. And I can show you here an example from a company, which is a spin-off company from NGI. We actually have airborne electromagnetics methods in ground investigations, where we send our helicopters, which attacks with equipment like this and scan the large areas. And Samson have talked a lot about the quick light challenge in Norway today, and this is what we were trying to detect, trying to find quick light in the ground with airborne electromagnetic methods, where in this figure it's just a 3D volume grid of electrical resistivities. From that, with a certain signal, they can rule out that is not quick. Some areas they can know straight up, they know for sure that is not quick light areas. And then for the area where the possibility for quick light, they can actually compute possibilities for this type of clays, like how sure, 80%, 90%, or 100% quick light. And then they can extract a volume where weak and sensitive clays is expected. And it is extremely useful for road building projects. Because in Norway, in many cases, when you build road through quick light area, it is either not doable or is increase the cost by 3-4 times. It make it impossible. So this basically initial scan to kind of detect roughly where the kick light is extremely useful. And then after that, we as geotechnical engineer can send out jury to kind of confirm if the signal is correct or not. And then imaging technologies. I mean, it's funny that I'm standing here because all the experts is sitting and listen, but it's, as I understand, it's a velocity measuring technique. Digital image captures either directly with digital cameras or by extracting frame from an analog video signal. An image is analyzed for position, displacements, velocities, and accelerations of the targets. I will provide it with some examples. This example from UNE-IFA is a 3D image-based motions analysis by TIAMA image system of a study of embankment settlement in centrifuge. And then this nice image is adaptive refined mesh topography for subsea cable breakout experiment. And here we have a photograph of a centrifuge model of slope post landslide in a centrifuge in an experiment that were conducted at University of Cambridge. And the systems shown on the right is a Raspberry Pi multi-camera photogrammetry system. And the results have been shown in one of the previous slides. Also, is the 3D point cloud of landslide surface with vertical displacement of raster map showing model scale movement from undeformed slope to post-failure surface. The conclusion is remote sensing, geophysical methods, and imaging technology offer great potential for cost-effective, efficient approach for monitoring of critical infrastructures, for characterization of subsurface, and detection of object defects and utilities. The main advantage is non-intrusive, non-destructive, and fast, and the possibility to cover large areas and challenging terrains which are costly or impossible to measure if using traditional methods. But there is real need for modeling in the lab and testing in the field, as well as research in data processing and to optimize their applicability in geoengineering challenges. And I won't go through this, but there is a table that we put in the report where we actually identify some areas that we could conduct future research activities as interaction between different geolab partners or through transnational access. And that is about it. I finished with my presentation.
Lei, thank you very, very much. We're just about on time. We've probably got time for a couple of questions before we break for lunch. So has anybody got any burning questions or comments for Lei at this point? No, I think everybody's very hungry. Oh, Yanis, yeah.
It's not really burning, but I can ask something.
Yes.
The various, thank you for a very nice presentation. The various geophysical methods that you showed, usually you can measure, let's say, shear wave velocity, VS or VP. Is it possible just with methods like this to, let's say, to get additional information related to strength? Or we always need some boreholes also?
I think he can reply to you because I really don't know.
Sure, Jens. Yeah, you know, for example, in Norway, there's NGI have a very nice large database of triaxial tests, and we've compared the data from their triaxial tests and their odometer tests to shear wave velocity measurements, and there is a very nice correlation between the two sets of data. So I think there is great promise in that.
Thank you. So you can use correlations that you have, but do you need to know the type of the material, let's say?
You do. Yeah. Unfortunately, those correlations are local. You know, so for example, the same correlation that we developed for marine clays in Oslo doesn't apply to the marine clays in Gothenburg, even though they have a similar geological background. So you need to be careful. The correlations are very powerful, but you need to develop them locally.
Thank you very much.
Nice discussion there. Any other questions? No? I think with that then, I will call a break for lunch. So thank you very much for attending this session, and thanks to all of the speakers.